Okay, good morning, Dr. Amrala and all my friends. So today, me, Wen and my friend Statistician will present about application of Q-meter. So first of all, I will show you about the basic circuit of an Q-meter. So a Q-meter actually consists of an oscillator. Then here is a low value resistance, and here is a resonating capacitor. So basically, the oscillator will act as a voltage supply to this circuit. Then the RSH, the low value resistance, is actually trying to short the terminal here. And here is a thermocouple voltmeter will be measure the voltage across the R and also the voltage across the oscillator. Then this resistance is connected like this. Actually, is to minimize the internal resistance in this circuit. Then next, the electronic voltmeter will be connected parallelly to the resonating capacitor to measure the voltage across the capacitor. And lastly, here is a test terminal. This is the terminal that we will connect the coin that we want to test to measure its Q factor. So actually, today we will present about the application of a Q meter. So a Q meter actually is mainly designed to measure a Q factor. So first of all, we have to know what is Q factor. So Q factor actually is defined as XL over R. So XL is actually stand for the impedance of the inductor. Then R is the resistance of the inductor. So I will briefly explain how it works. So first, we have to know that for a Q meter to work, is actually we have to tune the circuit to a resonance condition. So how to tune it? Actually, there are two methods. So first, you can vary the frequency of the oscillator until resonance, or you can change the capacitance of a capacitor to a resonance condition. So when there is resonance condition, it will provide that XL will be equals to XC. So since the capacitor and the inductor is connected series, so their current flow to them is actually the same. So we can also write like IXL is equals to IXC. So as soon as I mentioned, an electronic voltmeter will be measure the voltage across the capacitor. So we can, with IXC, we can return also equals to VC. This is voltage across the capacitor. So next, as we know that the Q factor is equals to XL over R. So now we times the both sides with I. It will equals to IXL over IR. So as I mentioned just now, IXL is actually equals to VC. Then IR is actually equivalent to the supply voltage. So the supply voltage is actually the V. So from here, as just now I mentioned, the VC we can get from the electronic voltmeter, and the V we can obtain from the thermocouple voltmeter. So from here, the Q factor can be determined. So.
Hi, so I will discuss about the operation of Q meter. So basically, Q meter has a minimum tunable RF generator, and the generator has a very low impedance output, and the detector with a very high impedance input. And then the calibrated amount of high Q capacitance across the component under test to allow inductor to be measured is another provision to add on. And then the next one, as we mentioned before, the generator is set in series way with the tune circuit, the national circuit formed by the component under test. And then the generator also has negligible output resistance, and the detector measure the voltage developed across one element, and the element is usually the capacitor and being high impedance in short. And then both of these actions does not affect the Q factor. So by scaling the detector voltage, Q factor can be directly read by the ratio of the level RF voltage to the applied RF current. And then this coupled with the knowledge of the reactive impedance from the resonant frequency and the source impedance. So I will continue the application of the Q meter, which is our title. Okay, basically Q meter have 5 applications. The first one, of course, is measure Q. The Q is quality factor. So basically, the Q meter can be check the Q factor of the inductor. So as mentioned in the introduction before, the Q factor is a dimensional parameter that indicates the energy losses within a resonant element. So it must be computed within a resonant circuit. And then in particular, Q is often used in association with an inductor. So as the internal tuning capacitor has an A dielectric, the losses existence is negligible compared to that of any inductor, and hence the Q measure is that of the inductor. So basically, I will proceed with the formula of the quantity factor. Okay, as you can see, Q is equal to 2 pi multiplied with the peak energy stored and divided by the energy dissipated per cycle, which we call power energy loss. And then this expression is applied to the RF generator, as we mentioned in the operation, and microwave filter, bandpass LC filter. After that, it also can be applied to an inductor or capacitor at the chosen frequency, which means the resonant frequency. And then for the inductor, the formula is, as mentioned before in the introduction by Wei Jun, Q equal to XL over R, between W omega L over R. This XL is the reactance of the inductor, and then the omega is the angular frequency, and the R is the resistance of the inductor. After the Q meter is worked under a principle which called Q equal to F over BW. F in this case is resonant frequency because we compute the Q factor in the resonant circuit, and then the BW in bandwidth of the filter. Okay, next, this is the first application of the Q meter. Okay, next I will continue the second one. So Q meter can actually measure the unknown impedance. So the method used in Q meter is by series of shunt substitution rate. It depends on the value of impedance. Let's say the impedance value is very low, we can use a series method. In other words, if the value of the impedance is quite high, we can use the shunt substitution rate to measure the unknown impedance. And then the third one is characteristic impedance of a transmission line can be measured using series substitution method. Okay, after that I will continue the fourth application of the Q meter. So besides this one, first one we mentioned the measurement of the quality factor in terms of L and R. This one we have to continue for the measurement of quality factor involving comparison of inductance and capacitance. Okay, the last one is the last application of the Q meter is to measure the capacitor, but only in small value. So basically, as we mentioned before, the capacitor sample must be in a resonant frequency with the cited inductor. L and C must be in resonant. So by adjusting the source frequency and using a tuning capacitor, there are two ways set to a low value on this calibrator scale. After that, the sample is disconnected and using the only same frequency. And then the tuning capacitor is decided to obtain a resonance again. So the difference in tuning capacitor calibration rate for the two tests is equal to the capacitance of the sample. So for the case of larger capacitor, source frequency need to be adjusted in order to obtain the resonance on the second test and manipulating the resonance formula. That's all for the application of the Q meter.
Okay, so now I will make a conclusion. So for conclusion, Q meter is mainly used to measure the Q factor at resonance condition. Next, Q meter can be used to determine the unknown impedance. So besides that, Q meter also can be used to determine the characteristic impedance of a transmission line. And moreover, a Q meter can be used to determine the quality factor involving comparison of inductance and capacitance. And lastly, Q meter can be used to measure capacitance in small value. So that's all for our presentation.